Picture this for a second. A state-of-the-art spacecraft currently in orbit. It's blasting hundreds, maybe even thousands of noisy, messy telemetry metrics back to Earth every single second. We're talking temperatures, voltages, thruster outputs, orbital positions. It is an absolute avalanche of numbers. I mean, how on earth, literally, do we handle hundreds of overlapping satellite sensors without just completely losing our minds?
Well, welcome to this explainer. I am absolutely thrilled you're tuning in because we are going to tackle that exact problem today. Our focus is all about transforming this overwhelming, chaotic stream of spacecraft data into clear, actionable insights, and we're doing it using a remarkably elegant mathematical tool.
Now, don't worry if the math sounds a bit intimidating, because here is our roadmap. 1. The big data problem. 2. What is PCA? 3. The mechanics of PCA. 4. Decoding outputs. And 5. Space systems in action. We're going from the core problem all the way to actually reading the final graphs.
Okay, let's dive right in with Section 1, the big data problem, conquering high dimensionality. Let's confront our main villain here, data overload in space systems.
Think of your data kind of like packing for a complex space mission. Imagine trying to juggle 20 loose, messy sensor variables in your hands as you walk out to the launch pad. You know you're going to drop something, right? It's inefficient, and quite frankly, it's exhausting to manage. But what if you could expertly pack 90 to 95% of the absolute most important information from those 20 items into just 3 neat, highly efficient bags? You'd be carrying a fraction of the bulk, but you still have almost everything you need to understand exactly what's happening.
Moving to Section 2, what is PCA? Defining the hero. Let's define the specific superpower we use to pack this data so efficiently.
That superpower is called PCA, or Principal Component Analysis. It's a statistical technique used to reduce the dimensionality of data while preserving as much information or variance as possible. And preserving really is the key word here. The entire goal is shrinking the size of the dataset without actually losing the true story the data is trying to tell us. We take a bunch of original variables and transform them into a smaller set of new variables called principal components.
Let's show a little empathy for our data here. Take spacecraft battery voltage and spacecraft battery current. A lot of the time, these variables are highly correlated. They're basically dancing to the exact same tune. So analyzing them as completely separate entities just creates unnecessary work. PCA recognizes this relationship and neatly combines them into one single principal component that captures the overall battery state. It realizes that these two sensors are really just telling us one unified story.
So you might be wondering, why go through all this effort? Well, a few big reasons. First, data reduction, converting something like 20 variables down to 3 while keeping the vast majority of the info. Second, visualization. Our human brains just can't picture 20 dimensions, but we can easily look at a 2D plot of PC1 versus PC2 to spot hidden clusters. Third, noise reduction. Components that explain very little variance are usually just system noise, so we can happily toss them out. And finally, feature extraction, which is absolutely critical for things like space weather studies, fault detection, and prepping data for machine learning.
All right, Section 3, the mechanics of PCA, how the math works. Let's see how this actually builds mathematically.
The math basically sequentially hunts down the patterns in your data. Step 1 is finding PC1, which is the direction in your data with the absolute largest variation. If your data points lie roughly along a line, PCA finds that direction and crowns it the first component. Then, step 2, it hunts for PC2. This is the direction with the second largest variation, but it has a super strict rule. It must be exactly perpendicular, or at a 90-degree angle, to PC1. Then step 3 finds PC3 with the third largest variation, and so on. It builds these components step by step so they never overlap in the story they tell.
Ultimately, what PCA is doing is finding entirely new axes that maximize variance. Think of it as a rigorous trial the raw data goes through to become purified. In practical terms, your software calculates this through powerful algorithms like eigenvalue decomposition of the covariance matrix, or singular value decomposition, commonly known as SVD. And honestly, it's pretty wild to think the core math for PCA was invented way back in 1901, long before computers existed. Yet it's exactly what we rely on to monitor modern satellites today.
Moving on to Section 4, decoding the PCA outputs, reading the results. I know terms like eigenvalue decomposition sound a bit intense, but we are going to anchor that math directly to what you'll actually see on your screen. Let's completely decode the terminology you're going to see when you run your software. When the program finishes, it spits out principal components, which are just your new transformed variables. Eigenvalues simply represent the raw amount of variance explained by each of those components. Loadings tell you how much each of your original sensors actually contributed to creating the new components. Scores are just the new coordinates of your data samples in this newly created PCA space. And the explained variance ratio, that's the really big one, is the simple percentage of the total story that each component successfully captured.
Now, you'll typically use 3 specific plots to visualize those outputs, which translates all those raw numbers into visible trends. The score plot is fantastic because it shows you the clustering of your observations. You can literally see normal operations clumping together and anomalies drifting away. The loading plot visually maps out which of your original variables are driving each component. And the scree plot, that's just a simple line graph showing how much total variance is explained by each successive component, which helps you decide exactly how many components you should keep.
Finally, Section 5, Space Systems in Action, a practical GNSS example. All right, it's time to bring it all together. Let's apply everything we've learned to a real-world space dataset.
Imagine you're working with a Global Navigation Satellite System, or GNSS, dataset. You're tracking 6 specific variables: carrier to noise density, the multipath indicator, signal to noise ratio, elevation angle, ionospheric delay, and tropospheric delay. Trying to analyze all 6 of these fluctuating variables simultaneously to determine the health of the signal? That is a massive, headache-inducing task.
But watch what happens when we run those 6 variables through PCA. The story simplifies beautifully. Instead of 6 chaotic lines, PCA groups the underlying patterns. It reveals that PC1, which accounts for 60% of the data's behavior, is really just representing an overall signal quality factor. PC2, capturing 20%, is clearly grouping together atmospheric effects. PC3, at 10%, accounts for geometry effects. And that final 10% is just unexplained system noise.
Just look at that number, 90. A staggering 90% of the variation across all 6 of those highly complex GNSS variables is explained by just 3 principal components. That means we can safely ignore the remaining 10% as noise, focus purely on these 3 new components, and confidently know we haven't lost the narrative of our telemetry.
To summarize, this is definitely not just an abstract math exercise. Whether you're working with GNSS, building spacecraft digital twins, or monitoring satellite health, PCA is absolutely vital. It's how you identify the dominant factors affecting performance, reduce massive datasets into manageable chunks, and crucially, how you extract clean health indicators before you ever feed your data into a machine learning or remaining useful life model.
So, I want to leave you with this final thought. How are you going to use PCA to uncover the hidden story in your own high-dimensional datasets? The next time you're staring at an overwhelming spreadsheet, just remember that the true narrative is in there, waiting to be unpacked. Are you going to let that data go to waste, or are you going to run your first decomposition today? Thank you so much for joining me on this explainer, and happy analyzing.